Seminar. Our first speaker today is a co-host of the Crunch seminar, Zongren Zou. He's also a PhD student at the Crunch group at Brown University, and he would be presenting to us a paper review on the topic titled Neural Architecture Search for Pins. With that, you may want to start, Zongren.
Okay, let me put it full screen. Can you see my screen in full screen mode? Okay. Yeah, hello everyone. Today I'm going to give a short talk on the neural search for physics-informed neural networks and a few related papers. So neural architecture search has been a hot topic since in recent years. I think since 2016, and people have been focused on finding the good architectures and then for single talent. So some people consider neural search as some people think it belongs to meta learning as well, because it learns to find a good architecture, and so it falls in the category of learning to learn. So but and this is a figure from the reference paper Neural Architecture Search or survey, and it shows the three most important elements of neural search: the search space and the search strategy, and also the performance. The performance estimate strategy. So most papers focus on this part of the search strategy, and they develop different methodology to find the best architecture efficiently. So the search space is the space of architectures you wish to search. So it could be a space of different architecture, different activity functions. Would be a space of different neural networks with different width and depth operations. And for performance estimation strategy, it is really simple in the computer vision, computer science community. So it's just how it performs on validation data. So normally what people do in machine learning when they have a data set is often split it into training data, validation data, and also testing data. So the performance estimation, the architecture is found on the training data and untraining data and validation data, and then it is tested on the testing data. So it's not an issue. It's not a big issue in the from the computer science community, but it turns out to be really big issue in physics from neural network. When you saw in neural network, so in PDEs, I'll discuss this issue later. So right, so here you see that this capital A is one specific architecture, and the performance estimation is performed on this specific architecture, and then the search strategy use this estimation to update the architecture to find a better architecture. Okay, so I think this paper is not perhaps it's not the first, but I think it's the first popular paper on this topic of neural search, and it is done in reinforcement learning, and so this paper was put on archive in 2016, and it was accepted in 2017. And in this work, a controller is used to sample the architecture. You see that because the neural network is a sequential model, so one layer follows the previous layer. So, and for each layer, there are many hyperparameters to search, such as this is for convolutional neural network. So we have the convolutional filter and the height of the filter, the width of the filter, and also the stride, the height and the width of the stride. Number of filters needed to be found in convolutional neural networks, and they use a controller to sample the architecture. So this controller itself is a recurrent neural network, following the sequential nature of architecture of neural networks. So and for each cell of the recurrent neural networks, it outputs and then the prediction is the output cell is fed into a softmax classifier, and then the output will be the discontinuous value of this specific hyperparameters. So the search space of this paper is in fact, a discontinuous searching space, you can see that hyperparameters hyperparameter is a discrete constant, and because the reinforcement learning is applied, so the policy gradient is used to update the controller. So in the end, a controller to sample architecture is trained, and then people wish, the authors of this paper wish to, wish that the controller can sample the good and the best architecture for the specific task. So the main problem of this, actually, this method it can give us really good architecture, but the problem with this architecture, neural architecture search method, is the computation time. So this figure, this table comes from the other paper, not this paper. So it shows the computation time on CIFAR-10 classification. So back in 2016, I think CIFAR-10 was already a non-huge problem. So the data set was not that huge back in 2016, not to mention now. So you can see here those two records the computation time for neural network search method with reinforcement learning. So here they use 800 GPUs for 3 to 4 weeks for this CIFAR-10 classification problem. So the computation time is really a huge issue, and yeah, so that's the main problem of this reinforcement learning technique for neural architecture. The main problem is every time an architecture is searched, a neural network with this architecture is trained from scratch, and then it has this the evaluation is done on validation data, and that one is considered as a reward for this controller or for this specific architecture. And then the controller use this reward to update its own parameters with bias, such that it learns to sample better and better architectures. So the most computational, the most of the computation is on the training of neural network with specific architecture. So for each sample from the controller, a training from scratch is done. So that's computational consuming. And similar to this neural search with reinforcement learning technique, another paper, I think with the authors, those two authors are the authors of this paper as well. So instead of the entire architecture, neural architecture, the way to depth, the convolution operations, all the other hyperparameters, this paper focuses more on the activation functions. And the same strategy is used, the reinforcement learning, and the same type of controller is used to sample the good, to sample the architecture for the active function. The active function is not a simple argument. It looks like a cell of convolutional neural network, but again, instead of the entire architecture, it only searches for the activation function, and the switch active function here was originally proposed in his paper, and authors claim that the searched architecture is actually working way better than the Waterloo active function in deeper model. So there's similar ideas on the activation function using the similar methods. So so to resolve the computation issue from the original neural network search with reinforcement learning, this paper proposes a new method, the similar methods, but now the parameters are sharing. So the table compares the computer time is actually from this paper, and then using this the efficient NAS method, the computer time is decreased significantly. So here you can see the original neural search about 800 GPUs for 3 to 4 weeks, and this efficient neural search is using 1 GPU, and it's much faster than the previous one. And the authors claim the error is smaller. so the key idea of this method is, remember in the previous method, the most computation is on retraining neural networks. So in this case, the neural networks actually, the weights and bias are shared among all the architectures. So different from previous one, in this one, a computational graph is created at the beginning of this searching. And for the, let's use this one as an example. So this is a computation, for instance, this is a computation graph. There are many 4 nodes on the computation graph. And instead of learning the width and depth, the sequential model of neural network, this method learns the connection among nodes. So, for instance, whether this connection exists, whether the connection from node 2 to node 3 exists. So it searches for this kind of architecture. And at the beginning, as I said, the computational graph is created, and each connection has its own weights and bias, has its own neural network parameters, and those parameters are actually shared among all possible architectures. So here, in this case, the architectures are actually subgraph of the original computing graph. So, and the authors of this paper believed that this shared parameter, do not really harm the performance of the search architecture. So, and the similar thing is they still use a controller. So this is a controller, which is a recurrent neural network. And they still use policy gradient to train the controller, with the wish that a controller in the end can output good architectures for neural networks. And in this case, a recurrent neural network, the architecture of a recurrent neural network is search. So to be clear, there are 2 neural networks. One neural network is the target neural network, and the other neural network is the controller neural network. Controller neural network is the one which outputs the architecture, and then the target neural network is the one used for a specific target, like classification, the segmentation, the detection. So in this case, the target neural network is recurrent neural, and the problem is about neural language processing. And so you can see this is the state from the previous, because this is recurrent neural network from previous cell, and this is the element of the sequence. So in this case, it learns connection inside every recurrent neural net, every cell of recurrent neural networks. And yeah, so this parameter sharing is done in this method, and the architecture of the neural network and the weights of bias, the parameters are updated at the same time. They're updated alternatively, but it doesn't require retraining for each architecture. So this is why this method is way more efficient than previous neural network search method. And okay, and this ideas of parameter sharing and not doing this retraining for each architecture are widely used in neural network search for efficient neural network search. So this paper is also, the DART's differentiable architecture search is also highly cited. And I forgot to mention that in the efficient neural network search method, the searching space is still discontinuous. The searching space is about the connection among all the nodes. So of course, connection is either there or not there. So it's discontinuous. And this paper, this DART's paper, instead focus on continuous searching space. So the difficulty, the main reason why in previous 2 papers people use this reinforced learning is that it's hard to gradient descent on discontinuous parameters, like to find the connection, like for instance, to find whether this connection exists. It's really hard to do gradient descent. And then if gradient descent cannot be applied, then how do we learn this connection? That's why they use reinforced learning and another controller to deal with this discontinuous searching space issue. And the DARS method, solve this discontinuous issue by relaxing the discontinuous search space to continuous searching space. So, and still primary sharing and this predefined, pre-created the computation graph are used. And so still for the neural network, for the architecture, it has for the neural network architecture, the neural network has 4 nodes, and the connections are to be determined. So here, and this is figure from the DARS paper, and they assume that maybe there are 3. Like, let's consider this as a neural network. So this is the input layer, and this 0 is the input layer. This 3, this 0 is input. The 3 is output. So of course it's not the regular sequential neural network model. So there's connection between 0 and 3, and so it could be, let's say in ResNet there's a skipping connection, or it could be different activation functions. For instance, from 0 to 1, from node 0 to node 1, it could be hyperbolic tangent, it could be ReLU, it could be linear, meaning that there's no nonlinear activity function. So those are to be determined. And so so basically from 3 operations, 1 operation is kept, and after the pruning we have this architecture, and this architecture is searched using this method. So the way the DARS method does is relaxing the discontinuous stuff to continuous stuff. So here O denotes the operations, such as like if we're searching activation function, O could be different active functions, could be, so in this set, this set could contain, let's say, hyperbolic tangent, ReLU, sigmoid, switch, and this X is after the linear transformation. So this O is a nonlinear active function. So, and this alpha denotes the alpha represents the architecture. So you see that it relaxed using the alpha is continuous variable, and a softmax is applied such that the coefficients of the operation are normalized, and and so it determines. So now we have a bi-level optimization, and the omega denotes the neural network architecture, and the omega star is the minimizer of the regular loss function. So here the training data is used, and this part is represent regular training of the neural network. So omega star is the minimizer of the Wilson bias, and alpha denotes the architecture. So here, so it's very clear that the problem is formulated correctly, that we wish to find alpha such that the minimizer of the Wilson bias to the training loss function, with this alpha we have the lowest validation error on the validation data. And still the bi-level optimization problem is really hard to solve, and if for each alpha the omega star is solved by training the neural network from scratch, then the method turns to be, it becomes really computational inefficient. So to deal with that, the authors of DARS propose this approximation, that the omega star is approximated by 1 step of gradient descent on using the training data, using the training loss. So you see here is the regular gradient descent update in the regular training of neural network, and the authors of this paper use this to approximate the omega star, the real minimizer. Of course, it's not a good approximation, and then this C represents the linear rate. And so this is the algorithm for darts. So we see that the alpha, which is architecture of the neural network, and the omega, which is neural network parameters, are updated alternatively. And after the training, the final architecture is derived based on the alpha. So the authors of the paper realized that the bi-level optimization problem solved in this way, of course, is not guaranteed to be accurate. So for instance, for this simple bi-level optimization problem, different value of this C, which could be considered as the learning rate of the inner update, leads to totally different results, different value, different results. So some converge to the right one, some does not. So this is the issue of the bi-level optimization solved in this way. But anyway, it works for neural networks because frankly speaking, in training neural network, we don't, most of the time we don't convert to the even to the global to the global mean to the local mean. Sorry. And here are some remarks on this DARS paper. So in the end, top K operations are kept according to alpha to derive the search space. So from this figure, it shows only one operation is kept, but actually in the results, in the experiment section for this paper, two operations with highest alphas are kept for the architecture. And second remark is the search architecture is retrained from scratch for testing. So this is, I think this is often overlooked by a lot of people, that this neural architecture search process results in alpha, different values of alpha, and also the Bayes bias. So of course it can be used to make prediction. It can be used for inference, but that's not how DARS does. So in DARS, the search architecture, the architecture is derived from alpha, and then the search architecture is retrained from scratch to compare with other architectures manually chosen. So this is very important. And the third remark is there's no strict stopping of the training of DARS. So here, this is a figure from the DARS paper, shows that the error decreases when the GPU hours increase. So meaning that the longer it is trained, the better result. In general, the better results are. So for bi-level optimization problem, because it is solved in this approximation, it's really hard to know when to terminate the training. And yeah, so those are three remarks from the DARS paper. And now let's move to the neural net search for solving PDEs, neural networks for PINs. I think there are two key questions from the NS community. One is, what is searching space? So in the previous three papers I show, the searching spaces are actually different. For the first one, the searching space is about the hyperparameters for the convolution operator, for the convolution operation, and such as the number of filter, the height, the width of the filter, and also the height and the width of the strat. So, and in DARS and efficient NS with parameter sharing, it's different. Now the search space becomes a space of connections. So the Bayes bias are there. There's no sequential model. The connection operations among nodes are to be searched. So for pins, normally we don't really have this special operation. We don't have convolution. We don't have pooling. We don't have this strat thing to be determined. So it's really important to clarify what type of stuff we want to search for pins. And the second question is, how do we evaluate the performance of architecture? So in the previous previous three papers, it's not actually an issue. They just for different architecture, in the end, when they compare the architecture from the neural active search and architecture from human beings, they evaluate in a way that, you know, we just train them on testing data or on validation data, and then we compare the results. So this is very reasonable, because in the searching process of this architecture, it has actually seen the data of the training data. So it's not fair to use the training data to evaluate the performance. So this is actually not a big issue in computer vision. But like I said, I think in the second slide, this is a big issue in PINs, at least for 4 problems where we use neural networks of solving the PDEs. So this paper was put on archive recently, named Neural Architecture Search Guided Physics from Neural Network for Solving PDEs, NAS-PINNs. So this paper used the DARS method to search for the architecture for pins, and the target is to search for the depth and the width of the pin. So the searching space now is a space of neural networks with different depth and width. Like I said, because they are not, we don't really use that any other types of operation. Normally we just use fully connected neural network for pins. Okay, so and to search for the depth and the layer width of the pin, the problem now becomes depth and width are discontinuous, and DARS, how to use the idea from DARS to relax the depth and width to continuous variables. And the authors of this paper used this type of technique, the masking for width and the skip connection for depth. So let's say here the G1, G2, G3, they're constants, and of course here we have 3 neurons, here we have 4 neurons, here we have 5 neurons. Because remember the DARS, the operation, the output is a weighted summation of all the different operations, and those, of course, those 3 cannot be summed up. So to solve this issue, the authors use this padding stuff, using this using masks to do this padding. So of course the 3 neurons cannot be added with the 4 neuron. They just add 2 here, and of course they are 0 out. And then for the 4 neurons, 1 neuron is added here, and of course it is 0 out. So in the end, using this technique, masks, those mask 1, mask 2, mask 3, they are predefined. For this case, there are 3 different weights to be searched, to be determined, and G1, G2, G3 correspond to the alphas in DARS. So yeah, and for the depth, they use this skipping connection. So if the A1, like say A1 is close to 1 or is much larger than A2, they're both non-negative constants. So I should say scalars. Then there is the skip connection, meaning that for this part there's no nonlinear activity function, so the depth is shrinked by 1. And okay, so here this G1, G2, G3, and A1, A2 are considered as architecture parameters, and this W and B are considered as N parameters, and of course they are shared among all the architectures, the same as DARS. So here I quote the sentence, one sentence from the DARS paper, from the this NAS-PINN paper. They call ANG as alpha, which is architecture parameter, and WB at theta, which is the N parameters. So you see here from DARS, theta corresponds to this is omega, and then this alpha corresponds to this alpha. Okay, so so this is how they formulate the problem. Basically the same as the same as DARS. So for theta star, which is the minimizer of training a neural network with a specific architecture, and here for the optimization of alpha, the architecture parameters, this MSE loss is used. So the inner loop is finding the best theta, finding the best parameters, and the outer loop is finding the best alpha. And for the inner loop, the loss function is regular pin loss. So here you see this is the PDE loss, this is boundary loss, this is initial loss. And for the outer loop is to find the best alpha, and the loss is the mean square error between the predicted U and the exact U. So I don't know if you if you realize the problem of this formulation. I'll discuss it later. So here is the algorithm of the NAS-PINN, and yeah, it's similar to DARS.
Excuse me, Zongren.
Yes.
Hi, this is Panos from Pacific Northwest National Lab.
Yeah.
So in this slide here, they assume that they have access to ground truth data, right?
Exactly.
So if you have, however, a problem where you only have the physics, how can you formulate a bi-level optimization? What would you use for the outer loop, for the alphas? Do they talk about this in the paper?
No. Panos, I think this is an excellent question, and I think this is the main weakness of this paper, that they uses they assume the analytic, or they assume the reference solution is known during this architecture search process. They didn't mention it, and they didn't resolve this issue. I think this is also a very key problem in neural search with pins.
Okay, thank you.
Yeah. All right, so yeah, so the algorithm of NAS-PINN is similar to the DARS. For every, so the n parameters are updated for n inner steps, and then the architecture hyperparameter, the architecture parameters are updated once. So and then in the paper, the author mentioned that if A1 and A2 are closed, skipping the layer and reserving the layer is both kept. It's like resonance. So remember that A1 is here, A2 is here. So if they're close, then both of them are kept. And if they are not close, just one is kept. So here, the first example in this paper is 2D Poisson equation on square domain. And the search space is, the depth is up to five hidden layers, and the width is 30, 50, or 70. And then the evaluation part, so the evaluation is clear in this paper, which I really appreciate. That in a lot of architecture related pins paper, it's not really clear, and I don't think a lot of them are done incorrectly. That the evaluation part for this one, the evaluation is clear. So architecture one, it's suppose we have two architectures, architecture one, architecture two. Architecture one is said to be better than architecture two if it has lower average L2 arrows from 5 independent trainings. So and then for this problem, they test all the possible architectures, 363 architectures, and they in this table they show the best 3, and they show that they claim that the NAS-PINN found the best one, and which is not the deepest nor the widest. So and it has the lowest L2 arrow, so it shows that NAS-PINN can deliver the best architecture. So yeah, and the second example is still 2D Poisson equation, but now they're on the irregular shaped domains, and the search space, the depth is up to 7 hidden layers, and the width is from 10 to 110. And because the search space is a lot larger than the previous one, so they didn't do they didn't test all the possible stuff. By the way, I really believe that this is how how architecture searching should be done. So for this case, actually the search space is of finite dimension, And so it means that we can test all the candidates architectures, and because of this, no method can beat the grid search method, right? The grid search method investigates all the possible stuff, and it is able to find the best one. So if the architecture, if the NS method is able to reach the level or the results of research, then it could be considered as the the method that works. And for this one, because of the the size of the search space is really large, so they didn't really test all the possible architectures. So they just choose 3 to be compared. And the name giant, dummy, and slender. The giant is the deepest and the widest. The dummy is the shallowest but the widest. The slender is the deepest and the least wide neural network. So I personally don't have a lot of experience on 2D Poisson equation for irregular shape domain, but I'm not sure if this L2L on the right are actually possible. So normally for Poisson equation, we can reach to 10 to the minus 3, 10 to the minus 4, but 10 to the minus 7, I've never tested it, but I didn't have a lot of experience. Yeah.
What is this notation with the groups in parentheses and then the 110 times 7? What does this mean?
For this one, I think it's just you can delete this. But for this, it means 7 hidden layers, each of which has 110 neurons.
And there's no special reason to have the parentheses and random groupings?
I don't think so. I don't think it's necessary.
Thank you.
Yeah, no problem. Okay, the third example is 1D progress equation with different viscosity, and they have the same search space. And from here, I do believe that those errors are too small. I think this is just my conjecture. They may. I think they forgot to take the square root. I think 10 to the minus 3 is much more reasonable for this type of architectures and for this type of viscosity. But also they tested on this 1D progress equation, and they shows that the NAS-PINN has the lowest L2 error compared to other manually chosen architecture. And they also have other examples such as 1D addition equation and also 2D progress equations. I don't have it here on the presentation, but it's similar. The results are similar. NAS-PINN, this shows NAS-PINNs are able to find the best architecture. Means that the architecture is able to find the architecture that has the lowest L2 error. So the key question here, I really want to discuss is, what is the validated data for PDEs with basically? So for pins, what do we supposed to do for the validation stuff? Because like panels just mentioned, especially particularly for solving PDEs, for doing 4 problems. And where we know the PDE, all the parameters, all the model parameter in the PDE, it's not fair. I believe it's not fair to use solution or partial knowledge of the solution in the architecture switching process. So here, this is a screenshot of the paper. So the author says the loss function for the in loop can be designed. So this is pin loss, and the loss for the out loop can be written as this MAC. This U hat is the prediction of pin, and this U is known analytic or numeric solution, and also N is the number of data points, and for the outer loop, blah blah blah. So for the outer loop, the required N can be rather small, but still the analytic or numeric solution of U is known. So I think it's extremely unfair, because for searching the architecture in the process, if the information from the analytical or numerical solution is available, then of course it can search. So we cannot really say that the searching strategy works, and it may be because that it sees some of the solutions in the training in the searching. So that's the main issue of this paper. And I think the main weakness of this proposed method. And but still the question remains, I think, when we use pins to solve PDEs, it's unlike a lot of supervised learning problems from the computer vision community. We don't actually have, of course we have the values of the solution at the boundaries, at the initials, but on the domain, we don't have any values of the solution. Then how do we evaluate? How do we do the validation? How do we do the outer loop? How do we evaluate the specific architecture where we don't have access to the solution of the PDEs? So I think this is, I don't see any papers resolving these kind of issues on neural search with pins. So I figure it's still an open question. Okay, so this is for the paper of NAS-PINN. And now there are a few other papers, architecture pin related papers. So one paper is this auto pin. I think the author of this paper gave a talk in Crunch a few months ago. And so the title is Understanding of Optimizing the Physics-Informed Neural Network, Physics-Informed Neural Architecture. And the search space is actually a lot broader. It involves width, depth, argument function, changing point. So here the changing point means the switching point between item and LBFGS. So normally when we train pins, we first use atom for a long time, for a certain period of time, and then we switch to LBFGS for higher precision. And the search objective is the smallest loss values reached by pins in the training process. So here you can see that you can see that it's no longer, the validation is not on the on this value. So here the solution to the PDE is unknown during the training process. And instead they focus on the training loss. They want to find the architecture that reaches the lowest training loss. They do that. This is written because of the observations they made in the paper, such as for pins, for each PDE, there's one dominant activation function, such as like for Burger decision, we have experienced that the hyperpentatives always works better than Waterloo because of the second order derivative. And the option 2 is under the after the dominant active function is chosen, then the larger changing points perform better. So the later you switch to LBIFGS, the better the result is. And also the option 3, the wider and deeper. I think there are 6 observations in the paper. And so based on the observations, they come up with this search strategy. So it's not, I don't think it's a neural architecture search. It's basically a strategy, a guideline on how to tune the hyperparameters of pins. So here the step 1, they first search the activation function. The step 2, they search, the step 2.1, they search for the width. They search the step 2.2, they search for the depth, and then they search for the best changing point. So the hyperparameters are decoupled, and then it was mentioned in the paper that this decoupling of different hyperparameters is done on purpose based on the observations, and so that will be another issue because people in neural search, those hyperparameters are obtained and tuned and trained at the same time. And the last paper I want, related paper I want to mention in this talk is the paper from Lulu, named Learning Specialized. It's about physics-informed activation function and to solve PDEs. So this is the one problem in the paper, the 1D Poisson equations, and then there are 2 specific problems. One with different source terms. Those the source terms have completely different behaviors. So they show that for this kind of type of problems, actually the type of activation function really matters. So you see here for problem 1, where the source term is summation of different sine waves, the sign activation function for the neural networks works way better than aberrant tangent than any any other activation function. And for the problem 2, because now the solution is of this format is it has exponential term in it. The exponential activation function works the best. Oh no, but the subclass also involves exponential inside of the activation function. And also for those two problems, the same PDE but different source terms, hyperbolic tangent both fail to provide good arrow. And so they propose this physically informed activation function like this. So it's very similar to DARTS. It's very similar to the NAS-PINN. So it's weighted sum of different candidates, weighted sum of all possible activation functions. So for the experiments, they used this 5 candidates: sine, hyperbolic tangent, J-Lu, switch, and subclass. And so they didn't really search for the best architecture. They used both. They used the weighted sum of the architecture. I'm sorry. They didn't really search for the best active function. They used more. And then in the end, so unlike DARS, where in the end, this summations or these operations are prone to maybe to just one active function, they keep them all. And for a lot of I think for all the different PDEs, different problems, the physically informed activation function have the best results and also the best average error. Okay, so that's basically it. Any questions regarding all the papers I mentioned in this talk?
Hi, Zongren, this is
Yes.
Panos again. Can you go back to the previous slide? So here, for the one that they say is the best, do they actually give the percentages, I mean, the values of the capital G for the final architecture, just to see what is the kind of mixture that gives the best results?
I'm not sure. I didn't check for that.
Okay.
I didn't check for that. But for the previous example.
But you say that they keep all of them according to certain probabilities that are given by capital G, right?
Right, but now because all of them are kept, so it's not probability.
Not probability, I
weighted.
mean the weight according to
yes.
the weight. So I just wanted to see if they have any actual values of these weights, just to see if there are some of them that dominate, or if there is more or less uniform distribution of weights.
They show it, no, they didn't show it in the example. In this example, they show that they use individual activation function.
Right.
There's dominant activation function for different type of problems. But I didn't check. I didn't check for this one. Yeah.
Okay. Thank you.
No problem. Any other questions?
Hey, this is Adar. Thanks for the presentation, really interesting. So I was wondering if maybe I missed it. The activation functions you're showing, is it like a part of the NAS, or it's just trainable activation functions like the adaptive activations? Yeah, like
it's just a trainable. It's not like DARS. It's not like NAS. So
okay.
I mean, yeah, it's just a weighted summation of different architecture. Oh, I'm sorry. I keep
that's an interesting
different activation function. Yeah.
Right. You can involve or incorporate the search for activation functions in the NAS, right?
Yes.
Or even like you could create some sort of an activation function that itself has some structure that you want to optimize for, not necessarily the weights themselves, but the architecture of the activation function. You know what I mean?
Yeah. But I think it's a quite interesting problem that in PINs we always choose universal activation function. We assume that every layer has the same activation function.
Right.
So yeah, it's not perhaps there's a better way to do that. That's one thing. Another thing is what you mentioned earlier. Yeah, I think right. We could search for maybe different layers have maybe like input layers has prefer some activity function, and the output layer, they have different preferences. Yes.
Yeah, that could be really cool. Yeah, thanks.
Right. Yeah, and the way they show it here for this example, actually, the activity function of the neural network has some physics information, have some physics meanings, if you look at this way. So yeah, because the solution for this problem one, there are a lot of sine waves, so it's intuitively reasonable to choose the sine as the activity function, right?
Right. Yeah. But what I'm looking for here is like, in P1, for example, your coefficients for the Fourier series is 1/i, which could be a trainable parameter as well. And the number of coefficients, like 20, you could make trainable and then incorporate the whole thing as part of the NAS, because it's essentially trying to figure out different structures of P1. Yeah.
Yeah.
And it's like a low-hanging fruit. Like, this should be very easy. Maybe not. I don't know. It might not be so easy to differentiate, but yes.
There are some ways to go around the non-differential stuff. We could relax it. We could use reinforcement learning. Yeah, and then that's interesting. Thank you for me.
Yeah, thank you.
Yeah, no problem.
Zongren, hi, this is Yanis. Thanks for the talk. I missed the beginning. I hope the question was not answered then. Two things, one question, one kind of statement. We've searched for architectures, not specifically for pins. One of the questions is, I always felt that there should be more work on mixed integer optimization. That is trying to do underestimators and so on and so forth. That is, you use global mixed integer optimization in order to try and look at architectures. I wanted to ask you, and maybe you said it in what I missed, if you find people that are searching using mixed integer techniques.
No, I haven't seen any papers on that.
Okay.
I understand the mixed integer problem is very useful. Yeah, go ahead, Dennis.
No, that's why. So I am hoping that the problems that are solvable will have some special structure, and then people may have some experience about it. So that's why I was asking. Also, another integer decision is whether you include any recurrences in your networks. What you showed while I was listening, they were all feed forward. I don't know if there were any decisions about whether the output of the third layer goes back into the second in some form or so. Did you say anything about recurrent searches for recurrent architectures?
I'm not updated on this field, so you can see that all the new active papers are they were.
I'm just asking. No, you obviously looked at the papers more than I have, so I'm asking somebody. Okay, and then the last thing, which is more of a comment, we have some experience in searching for algorithm architectures. And when we started it, we were hoping that we were going to find something interesting in general that nobody had found before. And in the end, what we found is that the result of the optimization is unbelievably sensitive to which class of problems and which class of sub-problems and which range of parameter values and which length of boxes you would have. So that somehow, unless you really know that you're going to solve this problem 10 million times, it's not so easy to kind of, get some rule of. I'm wondering if you have a comparable experience, or there was some place in which you found something that would be good for many problems at a time. Do I make sense in what I asked?
Sorry, Dennis, the connection is not very stable. So sometimes, did you catch the connection?
Yeah, so it's on my phone. What I'm asking is the optimization result extremely sensitive to which problem, which box, which parameter value you're with?
So actually, Yanis is asking, is there any global method which is not dependent on the problem type, on like the length scale parameter that you are using for your solution scheme, or is there any global scheme that can help search this architecture? Because in his experience, he has seen that they are very problem dependent.
It is very problem dependent. It is, but now,
Okay, yeah, thank
it is. Yeah, most of the methods are problem dependent, I think.
Okay, thanks.
Yeah, no problem. Sure.
Are there more questions for Zongren? Okay. So I think, thank you, Zongren, for this detailed talk.
Sure, I'll stop sharing. Yeah.
So we move to our second speaker. Our second speaker is Lena Podina, who is currently a PhD student at the Sheridan School of Computer Science in the University of Waterloo. And she has received her undergraduate degree from the University of British Columbia, Vancouver, Canada, in computer science. And she would be talking to us about universal physics-informed neural networks, symbolic differential operator discovery in biological sciences. With that, please join me in welcoming her, and you may want to share your screen.
Hi, thank you. Yeah, I will. Can you see my screen? All good?
Yeah, you may want to.
Okay.
Perfect. Perfect.
Yeah, okay. Okay, I'll start then. Hi, my name is Lena. Today I'll be talking about universal physics-informed neural networks. This is a joint work with Bryden Eastman and Mohammed Gahandal. So this is, I'm going to start with a bit of an outline for what I want to cover. I'm going to start with like an introduction, some motivation for our work. Then I'm going to get into UPIN implementation details. And sort of the latter half of the talk is going to be about applications of UPINs, kind of mostly in the biology area. So this is mostly, so I'm covering work from our recent paper, which was accepted to ICML this year. So that will be up until Berger's equation. And then after this point, I'm going to add a little bit of detail on some more recent work that we've done for chemotherapy drug modeling. And this is not quite, is not published yet, but yeah, but it will go in a follow-up paper. Okay, we are the Mathematical Medicine Lab at the University of Waterloo. We focus on the mechanistic modeling of disease with focus on oncology. One of our aims is to integrate data-driven modeling with conventional differential equation-based models. This integrative approach, and I'll get into some detail about why, sort of reduces the manual building of assumptions in biology. The UPIN approach is fairly general, but here I'm going to focus on biomedical applications. So here's a motivating example. This is a pathway that shows the biology of apoptosis, which is programmed cell death. So it's caused by a regulatory network within the cell. By the way, I forgot to mention, if you have any questions at any point, feel free to just ask them throughout my talk. So it's programmed cell death. Essentially, there's kind of a regulatory network of a whole bunch of proteins. And the key proteins here are P53 and AKT, which P53 promotes apoptosis and AKT inhibits apoptosis. So those are kind of the key proteins. And the details here are not so important, but the pathway is essentially sort of fairly complicated and is not entirely well known. So as I said, the pathways are not well known and there isn't so much data that can be used in order to kind of validate it, but they can be modeled using a system of differential equations or a mechanistic model. So here on the right, you can see an example. This is the simplest model from this particular paper, which looked at stability in apoptosis. And here we just have sort of the key elements, P53 and AKT, the key proteins. And we just have like a fairly simple ODE here. So like a pro of modeling biological pathways in this way is that the model is very interpretable. It's white box, kind of every single equation that you code in there. You have to do it manually and from scratch, and you have to sort of pick the parameters. And you know kind of exactly what the mechanism is that you're modeling what's going on. But a con is that this manual incorporation of assumptions can be fairly time consuming. So you might have to go through a lot of literature. You might have to make modeling decisions. As I said in this paper, there are actually 3 different models that the authors looked at, and looked at basically bistability effects in each one. But essentially, when you're modeling, you kind of have to choose what level you want to model things at. So one of our sort of main questions that we're trying to answer is, can we use machine learning to identify these underlying mechanisms of action? So this brings us to kind of a kind of emerging in popularity research direction in biological modeling, which is the integration of ML and mechanistic modeling. So of course, white box models can be time consuming to create and can be also fairly complex to analyze. But on the other hand, if you just have kind of a black box model, such as a neural network, it can be just fairly uninterpretable to understand what's going on. Gray box models kind of balance the role of data and physiological knowledge within the model. Also kind of branching off of that, we have quantitative systems pharmacology, or QSP, which is essentially mechanistic modeling, which in sort of the drug development area. So applications are predicting drug toxicity, efficacy, and also personalized medicine. So here, again, kind of a very emerging research direction, rather than kind of time-consumingly, painstakingly making these distilling literature and making assumptions, you can use machine learning to offload some of that burden. Some of the more common directions of integration are parameter inference, inference of model structure, and dimension reduction. So this brings me to a second motivating example, which is tumor growth modeling. So glioblastoma multiforme is an aggressive brain cancer. And one way that you can model it is using the PDE on the right. So this is the well-known Fisher diffusion proliferation equation. And here it has 2 parameters, the diffusion parameter and the growth parameter. And DNR can be used to predict tumor growth in response to treatment, but biologically, they're fairly difficult to measure. And you would also have to measure them per patient because every patient might have a different set of parameters. Meany et al. 2023 produces estimates of these 2 parameters per patient using 2 MRI images. And the authors use standard sort of physics-informed neural networks to obtain the parameter estimation. But there's kind of a significant pipeline that that the data has to go through first, from data acquisition to segmentation to figure out where the tumor is, conversion to cellularity or the number of cells, and then finally the last step would be physics-informed neural networks. However, a drawback of standard sort of PIN approaches is that they require the entire differential equation to be fully specified. So one of our questions here is, so this is a motivation for asking whether we can find the hidden structure of the model using machine learning. There has been existing work in this area, mainly in UDEs and neural ODEs. And what these methods do, they're kind of similar. They allow the fitting of functions or entire components of differential equations from data. And the way that they do that is they approximate these interactions with neural networks, basically. So here, if we have this this ODE here, which is the Luck-Volterra ODE, then they can just, for example, if this term is unknown, they can just replace it with U1 and then learn this universal approximator. So their method obtains a solution to the differential equation along with an approximation of these terms.
Hi, Lena.
Yeah.
This is Ameya. Can you go back to the previous slide?
Yep.
What do you mean by this traditional pin require an entire differential equation to be fully specified?
I mean by continuous physics informed neural networks, where you have where you're either solving the differential equation or you're jointly solving it while fitting parameters. So it's kind of the original kind of physics informed neural network.
Okay. Okay.
Yeah. So one issue that UDEs have is that they're not particularly robust to noisy data. So we tested this and we noted some mentions of this in our paper as well. They don't perform well on noisy data right out of the box. And if you can see here on the bottom row, it's essentially, even though the fit here on the top of the solution is pretty good, the hidden target or the hidden terms are not learned accurately. So biological data is often sparse and noisy, so it's important to address this problem. So we found, so this is an introduction to our method. Basically, we modify the standard PIN to identify hidden terms from noisy data. We provide the same type of solution as a UDE, but we found that it has significant noise robustness, and it can also, so it can perform well in sparse and noisy data essentially. And yeah, so this is the same data. It identifies it fairly well here. So overall benefits to using this approach or yeah, or UDEs kind of using these approaches is a better fit to the data than using a misspecified model. And also, we're hoping that we can discover biological interactions directly from data. The other thing that we did was we integrated, or rather, we just kind of added as a second step, this step of symbolic regression. So we took the approximation that we could get from pins and we ran it through a symbolic regression algorithm. Namely, we used AI Feynman. And symbolic regression algorithms essentially find a model for the data set in a symbolic form, right? And in doing that, they trade off complexity and goodness of it. On the right here, you can see a flow chart of how AI Feynman kind of works. So you give it some data, and then there's this algorithm that it kind of goes through. And then at the end, you can get an equation which hopefully describes your data in the simplest sort of possible way. And these methods can be used to discover physical relationships between quantities. So the next part here is going to be like an overview of continuous pins. I realize that most of you or all of you are familiar with them, but just for the benefit of anybody who isn't, I'm just going to go through it and then explain how our method is different. So here we're going to assume that we have a PDE, or so in this case it's a PDE, or you can have an ODE, and you have data from this differential equation. And the idea is to fit a neural network to the solution of the differential equation or create like a surrogate solution. And optionally, you can also fit parameters within the differential equation. So one way to do this is you can have two loss components, so the data loss and the pin loss. The data loss ensures that the neural network or the surrogate solution fits the data. And the pin loss ensures that it fits the differential equation. In our method, we make an extra assumption that the differential operator n here can be split into two components, a known component and an unknown component. We model the unknown component, and you can have, and later on we look at cases we have several of those. You can model that with a neural network. So basically, this is just a comparison. We can do basically what standard pins do. We can also fit parameters, sort of alongside creating the differential equation solution. However, as I said, we model unknown terms with one or more neural networks. We enforce boundary conditions with a third loss term, which you can also do in standard continuous pins. But in our case, you can also learn part of the boundary condition. So this is the loss function that we use. So here, very similar, we have the data loss, boundary loss, and the pin loss. So the data loss is exactly the same. We have a neural network for U. We have the data. The boundary loss, essentially, we're also able to use a third neural network if needed to model a part of the boundary. So if, for example, we have a known component of the boundary beta k, and we have an unknown component, we can model it with the neural network B. And this is kind of like a pin loss, but just for the boundary loss, and it allows us to learn part of the boundary condition. In the pin loss, it looks kind of like what you would expect. This is the auto-differentiated differential equation solution, and then nk plus f is the differential operator, and nk is known and f is unknown. So due to the fact that f is kind of in here, and you can differentiate the pin loss with respect to all of the parameters of f, then that way you can just fit the neural network via the pin loss. This is a diagram showing how you might implement this for ODEs. Again, sort of two components here. They're in green, and they represent neural networks to be trained. The surrogate solution basically takes time as input. The known components takes time as input as well. And then the unknown component can just take the prediction U as the input. And then these two things go into the pin loss. Meanwhile, the prediction U also goes into the mean squared error loss. And then that way you can get an overall loss which sums the pin and the mean squared error loss. So compared to the UDE architecture, so basically UDEs are ODEs or PDEs defined with embedded universal approximators or neural networks. However, there is a significant difference here, which is that neural ODEs or UDEs use the cost function of the distance or mean squared error only, and they do not use any kind of pin loss. So that's because the equation, the differential equation, is sort of by assumption it's enforced rather than in a softer manner as per pins. On the right here, I have like a neural ODE, which is a special case of a UDE. And in this case, we have basically a variable, and the entire right-hand side of this ODE is defined via a universal approximator or neural network. And then the way that you would minimize this kind of equation is using adjoint methods rather than solving the differential equation in reverse. Or sorry, so this is solving the differential equation in reverse rather than back propagating through the solver. So they developed a method to do this in, I think, constant memory time. So yeah, so the rest of the talk is going to be applications. So the first application that we use our UPins for are to learn the interactions in the Lotka-Volterra predator-prey equation. So we took the terms in red and we approximated those with a neural network. It could be two, but we used one. and with 2 outputs. And we fit it basically using the first 3 time steps of the data on the right. And this data was varying levels of noise and sparsity. So here we have 2 tables. The top one is for noiseless data and the bottom one is for noisy data. So for the top one, we're basically comparing different numbers of data points. So that's 1, 5, and 10, and also different numbers of collocation points. And of course, collocation points are the points at which the loss function enforces the pin loss. And the more that you have of those, the better your solution will in general be. And in this case, we see kind of a similar trend. It does improve as collocation points improve, but also with only 10 data points, we can get a pretty good identification of the hidden target, or these hidden terms. So we can get 10 to the -6. For noisy data, of course, we do slightly worse because simply because the data is noisy. And however, we still get fairly good identification of the terms here. So you've already seen part of this graph earlier, and this is when we ran UDEs on sparse data on the right and noisy data on the left. For sparse data, it tends to do fairly well. It does a good job approximating the differential equation. However, for noisy data, it basically fails to learn the hidden target. It also has some trouble fitting the differential equation without getting kind of affected by the noise here. We also ran our method on the exact same data, so sparse data and noisy data, and we notice pretty good results. We're able to recover the underlying hidden terms in the case of noisy data and sparse data. And also the solution here doesn't seem to be quite as affected by noise, so it seems to be sort of noise robust. This is a comparison for different levels of noisy data. So we have increasing levels of noise on the right, and we have increasing levels of spacing between the time steps on the left. And we ran UDEs and pins to see what the error was for each data set. So lower is better here. Pins tend to perform better than UDEs for almost all cases of sparse data. And they perform better on noisy data as well, actually. So this is the part where we ran AI Feynman, or symbolic regression, on the output of the approximation that we obtained from UPins and UDEs. So basically, we just gave it kind of as a data set. Since it's just an approximation, you can just treat it as a data set. And we gave it to AI Feynman and saw if it could recover the underlying functional form. So in both cases, the hidden term is CXY with some coefficient. And we see that, so the way that the rows work here is each row is a separate data set, so a separate test. So we have increasing levels of spacing with no noise, and we also have increasing levels of noise with spacing kept constant. So so F1 is the first term that we're approximating, and F2 is the second term, and we approximate those two together. And then of course we have UDEs and pins, and we ran sort of these two together and these two together. And basically, if we look at the results from AI Feynman, we're able to recover the coefficient fairly well in a lot of cases when we do it on the approximation from the UPin method. And dashes represent scenarios where the the symbolic regression was not able to recover the correct functional form. So yeah, so there's a lot of test cases here where it wasn't able to do it for U to E, but it was able to recover the coefficient to a high degree of accuracy for U-pins. The next application that we tested is the apoptosis equation that you saw earlier in the introduction. So this is the simplest model of apoptosis from that paper, and we simulated the data according to that model. And in two separate experiments, we replaced V1 here in blue and V2 with a neural network. Another detail here is that the neural network got all three variables as input. So we have P53, AKTS, and AKT, and it obtained all three variables, even though the function actually only is a function of two of those variables, and same for this one. So three variables here are P53, so active AKT and inactive AKT. So we use 30 noiseless data points, and we obtain a fairly good approximation here of 10 to the -4 for the hidden targets. The curves don't look exactly as sort of maybe they're supposed to in terms of the true interaction, but they kind of they're sort of on the correct order of magnitude, and the hidden target error is quite low. Yeah. So lastly, we tested this on Berger's equation. So here we have it. This is what we took for nu with periodic boundary conditions, and we took the known component to be nu ux x and gave u ux and ut as inputs to the neural network that models the unknown term. Training data was slightly noisy, and it was taken from t equals 0 and t equals 0.5, with basically positions sampled for each of those for each of those times. So just to kind of reiterate here, the hidden term is this one, and then we assume that we know this term, and this was modeled by the neural network. So we can reconstruct the PDE with a good sort of very small error. So we can reconstruct the PDE solution, and then also we're able to reconstruct the hidden term as well with a fairly low error. So that concludes the contents of the UPenn paper that has been published. This is kind of the new work on chemotherapy and drug action discovery. So, so I'm going to shift gears and explain kind of the ODE that we're using here. Essentially, we have N being the number of tumor cells through time, and C here is the concentration of chemotherapy. So N, we're going to assume is growing with logistic growth here. So kind of it grows more or less linearly, and then it plateaus. And the cells are basically killed as a function of the amount of chemotherapy and as a function of something else called the cell kill strategy. Chemotherapy here, we're going to assume just decays as a sort of proportionally to the number of cells and the amount of chemotherapy drug there is. So I'll show data for what this looks like, but essentially we just apply chemotherapy kind of once at one time step after the cells have grown, and then we see how they die and how the chemotherapy decays. So G of N here is going to be one of the log kill model, the Norton-Simon model, and the Emacs model. So these are sort of common ways to model the log kill. However, we're interested to know whether we can actually identify G of n from data. So G of n here, so log hill is just linear. It's just going to be a linear term. Norton-Simon basically is supposed to mimic the growth term, and then the Emacs model just kind of asymptotes here. And then, yeah, so are we able to identify the type of drug action from the cell count and drug concentration over time? That was the question. So usually G of n is kind of just assumed, but we're interested in learning that from data. So this is what the simulated data looks like. We have concentration of drug over time, C at regular intervals. So we just measure it. And then cell count also sort of measured over time. So this, like, if this was an experiment, this would be conducted probably in vitro. So here what's happening is we just let the cells grow. They kind of reach carrying capacity, and then we apply the drug, and then immediately they start kind of dying, and then sort of maybe going to zero, and then the drug concentration decays. So our approach here is to model CFT with a neural network and fit it using only the data loss so that we can interpolate CFT. This step could theoretically be replaced by any other fitting method, but we just use a neural network. Then we fit G of T and C using U-pins, and then we just divide by CFT to obtain G of T. If you wanted to, you could also kind of model CFT and G of n by separate neural networks. That worked too. I just found that it was a better result to model it as one neural network and then divide by CFT. Yeah. So basically, this is where we simulated different data. So we have log kill type treatment, NS type treatment, or Norton-Simon type treatment, and Emacs type treatment. And the curves look pretty similar, actually. But we're also able to estimate G of n, basically. And here, as expected, it's linear. Here looks kind of quadratic. And here, yeah, it looks like that. So we can basically fit this sort of fairly well. There's a bit of an issue fitting kind of the higher numbers of cells. So just from over here where the slope is really high. But overall, it does a really good job. The other thing to note here is that the spacing looks kind of like we're spacing it every constant amount of cells that die. So rather than spacing it in time, we're spacing it so that there's an equal number of points for each unit of slope. I did it kind of the other way as well, where you just take you just take points kind of every certain constant number of time steps. This particular method of acquiring data was a little bit more it basically resulted in a better fit because there was more information for the neural network to figure out what was going on when the slope was, when there were high numbers of cells. So perhaps it's not a realistic way of gathering data, but it sort of gives the neural network some more information over here. So we did the same thing for noisy data. So just added some noise, and again, sort of the result is understandably a little bit worse, the recovery, but we can still recover the drug action basically. So what this means is if you have an experiment where you have these cells, you grow them, and then you apply some drug action, you would be able to learn what kind of drug action that particular chemotherapeutic has on those cells, rather than making an assumption for which one it is. So rather than just modeling it with all three of them, you can figure that out from data. So here is a summary of our performance for identifying the drug action. Again, 3 different ways that we collected data or generated data rather. There's a case where we adjusted spacing, where again, I adjusted it for the slope. So there's a sort of equal spacing, which is where the data was collected at a constant sort of rate in time. And then there's a third case where I took this adjusted spacing and then just added noise. So the error kind of goes up as you sort of add noise, and then equal spacing performs worse than adjusted spacing. But overall, the error for all 3 drug actions is still fairly small. And as seen on the graphs, you can kind of see the overall shape as well. The other thing that we could do, and we were also able to do this. We're able to estimate beta from the untreated data using the standard sort of PIN approach, continuous PIN approach, and then fit the drug action using the estimate. So by beta, I mean this proliferation rate here. So you can do that. You can estimate beta and then use the estimate in your in the subsequent estimations of the drug action. So we were able to do that with a good accuracy as well. So this is another chemotherapy experiment that we performed. So this is kind of, again, in silico. This is all simulated data, but it would be cool to definitely to apply to in vitro data later. But essentially here, this is a slightly different setup. We still have number of tumor cells in time. We have a proliferation rate and we have a carrying capacity. So in the previous scenario, the carrying capacity we just assumed to be 1. But here we actually have a carrying capacity. So sort of the max number of cells that the medium can sustain. And we're going to assume that the carrying capacity and the growth rate both depend on the chemotherapy dosage. So, so this is, for example, when you give some cells chemotherapy and then after you remove it, and the chemotherapy sort of has this delayed effect and affects, kind of reduces the carrying capacity, reduces the growth rate. And the way that we modeled this was kind of in a PDE-like approach, where n is now a function of time and dosage. So that appears here. So we have a neural network for that as the surrogate solution. And then Kp, instead of being constant, it's going to be a function of dosage. Theta is a function of dosage as well. So these are the hidden terms. So we have one neural network to fit this. So it takes just dosage and it outputs the carrying capacity. And then we have a second neural network that fits the proliferation rate, which takes dosage, outputs the proliferation rate. And then the surrogate solution takes these 2 things, time and dosage, and then outputs the number of cells. So PINs can be used to fit a separate proliferation rate and theta for each dosage, but it would be fairly time consuming because you would have to just take every single data set, every single time series, and just do it separately. Kp and theta can be easily also interpolated between dosages using UPINs, and I'll show you what I mean by that. So this is what the data looks like. We have 11 points per dosage. So we have 15, 25, and 45 nanomolar. That's the concentration. And basically decreasing carrying capacity and growth rate as the dosage increases. We assume the same initial condition, and we see that for the surrogate solution, we're able to interpolate fairly well between data points. So here, this one is the highest chemotherapy dosage. This next curve is the medium chemotherapy dosage, and then this last one is the highest level. So yeah, and these are the interpolations between the data points for the surrogate solution. So this is another sort of explanation of what I mean by interpolation here. On the x-axis we have dose, so these are the true values or observed sort of values for, or true values for the observed dosages that we have. And then we're able to, because we're modeling this as a neural network, we can also say, okay, we have an idea of what theta can be between dosages, right? And even though there's no data observed, we can interpolate these parameters. So for example, for 20 nanomolar, even though we don't have data for it, we can interpolate it and say what the carrying capacity will be for that dosage. We haven't tested this, but I'm guessing that if you add additional constraints, like in the loss function, you can affect these interpolations so that you can, so that they're not just sort of what the neural network thinks should go between them, but perhaps something more, more constrained by underlying knowledge that you have. So this is where we identified theta and KP. So essentially, I talked about interpolation, but here the estimate also matches, right? For dose, for different levels of dose, basically. And what we did is we took those estimates and then just sort of integrated the resulting ODE to see how well it matches data. So because it's one thing if the surrogate solution matches the data, but it's possible that the surrogate solution matches, but the estimates in fact don't. But here in this case, for the different dosages, this is again lowest dosage, medium dosage, and highest dosage. We're able to match the true theta and KP, or proliferation rate, very well. So we get a 6 × 10⁻⁵ and -8 result here. The circuit solution, as mentioned in a few graphs back, also matches really well. The same thing can be done for noisy data. So here, theta, again, kind of quite understandably, the error is a little higher than in the previous slide, but it's still very, very good. So it's 10⁻⁴, 10⁻⁵. And as you can see, the estimated parameters, if you just kind of take those and just integrate them and see what you get a fairly good fit to the noisy data. So in summary, the UPIN method is able to accurately identify hidden terms from sparse and noisy data. There are lots of applications in ecology, cell biology, chemotherapy modeling. We also perform well on PDEs as well as ODEs. And finally, we link well with existing symbolic regression algorithms, such as AI Feynman. And again, here it's kind of useful at this point because you can link it to any algorithm that you like. Future work include applications to clinical and in vitro data, more specifically for this last project for chemotherapy modeling. The case where you have these different dosages, definitely it would be really good to apply this to in vitro data after we've done enough simulations. Another thing that we're interested in is combining symbolic regression and the hidden term approximation in one step rather than two. It could be possible that these two things can inform each other. And then lastly, we're also interested to know, can strictness of the differential equation constraints and locations of the hidden terms be automatically tuned? So perhaps there's some kind of search algorithm that we can incorporate, which would automatically sort of switch in and out some of these neural networks to see which ones, to see which terms are should best be modeled by the neural network and which ones should be sort of left alone. I think there's kind of an identifiability issue though that kind of comes up here, and it would also be interesting to sort of incorporate some kind of some kind of algorithm that looks at identifiability of these neural networks and whether the parameters can or the hidden terms can actually be identified. Yeah, right. So for my acknowledgements, thank you to Professor Mohammed Khandal and Professor Ali Goetze, my supervisors, Brian Eastman, my co-author on this paper, and Cameron Meany, my colleague, who published the work on the brain tumor modeling. And funding was obtained from CRHR and MyTax. Thank you, and that would be it for my presentation.
Thank you, Lena. That was quite a wonderful presentation. And, do we have questions for her? Probably we don't have any questions, and thank you for this presentation. So with that, we come to an end of our seminar today. I would be uploading the recording of the seminar on our YouTube channel, so please follow us there, and have a great rest of the day and a great weekend ahead.
Thank you so much.
Bye.
Yeah, thanks.